Okay, so we're going to look at problem 10.19. This problem is very helpful as you finish and prepare the homework for this week. So in this problem we're going to look at speccing out a motor for an auger application. So we're going to look at what motor we want. We're also going to then look at designing the motor circuit, okay, and selecting ratings for each of these components. So we'll start with the motor selection. I'll probably break this into two videos. So the application here is an auger. It's an 8-inch auger. It's on a 45-degree incline. It's stationary. The actual auger will run at 450 RPMs off a belt drive, but we want a motor that's a 1725 horsepower or a 1725 RPM motor. We're going to run that motor most likely 8 hours a day. So it's stationary. We're going to have conduit, rigid conduit to a electrical panel. Electrical panel is 120 240, single phase. We're going to use copper conductors in the conduit, and we're going to process dry corn. So let's start looking through the different things we need to look at when we start selecting a motor. First thing is, what type of motor? What kind of motor do we want to use to run this application? If we look at table 10.2 in our text, this table is very helpful in identifying just kind of roughly the motor types and then typical usage. And so if we scroll down the usage here, we have two different motors that are used typically for augers. We have a 2 capacitor value motor, and then we also have capacitor start induction run motors. So those are two common motors that we can use for augers. So this is a nice table to just get an idea what type of motor we would want to use. We can also look at Grainger. They have a nice interface for looking at different types of motors and different application scenarios. But based on table 10.2, so per table 10.2, we would look at either a capacitor start or 2-value capacitor. And those have to do with how the motors are started. So these are both single phase motors, and if we remember single phase, we can't just start it and expect the rotor to spin. We need some way, some mechanism to get that rotor to start spinning. So we can use capacitors as the most common way to start a motor, a single phase motor. Things go out of phase, things start leading and lagging and no longer in phase, and so there's something ahead of the other, we can get that rotor moving. So we would use one of the other, pick one of these, and we could look at Grainger and make our selection between a capacitor start motor or a 2-value capacitor motor. If we look at a horsepower, okay, here's where, depending on the application, we really got to be looking at the application, either the manufacturer's recommendations or some other tables or rules of thumb or what we've used in the past that has worked, or even just measuring and looking at the physics, right, and calculating. But for an auger application, there's some very nice appendices in the back of our book, especially Appendix A. And if we look at table A.2, it's approximate horsepower for each 10 foot of auger using dry corn and 450 revolutions per minute. So if we recall, we have 25 feet of auger length. It's a 10-inch, and we have a 45-degree incline. So when we look at our auger diameter, our 10-inch, we have a 45-degree incline. We would need a 2.5 horsepower motor to run that per 10 feet, right? So that 2.5 horsepower per 10 feet is what we would need. So if we turn back to our problem here, we would want to go and take 2.5 horsepower per the 10 feet times our 25 foot of auger length will give us 6.25 horsepower. Okay, so that's per A.2, right? Based on the horsepower per 10 feet, we have 25 feet. Feet cancel out, we're left with horsepower. Most likely, though, if we go and look at Grainger, we're not going to find a 6.25 horsepower motor. I believe we're going to find a 7 or a 7.5. Probably we'll have a 7.5. Okay. But we can look at that. We can look at Grainger. We can sort and filter by voltage or horsepower. Then we want to look at voltage. So what voltage would we run this motor at? Well, the concept is higher volts, lower current, right? Lower current, smaller conductor size. Smaller conductor size, less weight, less money. Okay, so that's the concept. I want to crank that voltage up, reduce the amperage, keep the conductor sizes small and cheap. So we're going to go with the 240. Okay, 240 volt single phase system. Okay, so 240 single phase. So when I go to get my motor, I want to look for a 240 single phase motor. So how many poles do I want? Well, I need to run the motor at 1725 RPMs, nameplate. Now if we look at table 10.1, we would find that a 4-pole motor will run at 1725. Okay, so we can use that table just to identify the RPMs of our motor. How about bearings? This is a little bit more subjective. However, we do have a table in our book, table 10.7. Pull that out here. And this is more of a just pros and cons of the different bearing types. Bearing versus sleeve, ball bearing versus sleeve. It's just a 1 is, good, a 2 is not good. So 1 is our best, 2 is our worst. It's just a pro-con, right? Looking at all this, looking through that, I would say that we would probably want to go with a ball bearing. So we'll do ball bearing. And this is based on less lubrication and withstands loads better than the sleeve. So that's just kind of a subjective, but we really want to just think of our application and think of the maintenance that's going to be required and the environment, really, right? And we could talk to, if there's a application specialist that we know from our vendor, we could ask them too. Mounting. So it's going to be solid, mounted solid, okay? Stationary. So probably a flange mount, possibly, maybe a foot mount, okay? But the mounting is going to be solid. And this really comes into play when we talk about our disconnect means in our motor circuit, whether we can use a plug or not, or actual switch disconnect handle. If we look at enclosure type, we could look at page 151 in our book, and we could go through and read through all the different types, or the very common types. There's more than this, but these are the most common. And looking at our environment, most likely it's going to be outdoors. So we're going to want something that's enclosed, a motor housing that's enclosed, possibly. We could maybe argue that it needs to be explosion proof depending on the scenario. We got to talk about that if that's something of concern. But we're going to assume that it's out of a lot of the grain dust environment. It's further away from that, out in the open. I would say totally enclosed air over, or a totally enclosed fan cooled Okay, and I might actually go with this because of the duty cycle, all day, 8 hours a day. Okay, so we have 8 hours a day. You know, we can get some hot fall days that we want to make sure we can keep that motor cool, and a fan will help us do that more effectively. So these are some of the things that I could select for my motor. I need to think about and have an idea of, what do I want when I go purchase that motor. Because when I go to Grainger, they're going to ask me those things, or I can use those things to pick out a motor, right? So voltage, 230, right? That's, you're going to either find a 230 or 240. You can pick shaft diameter. You can pick mounting. You can pick motor style. This is a capacitor run motor. You can motor service factor, ball bearings, motor bearings, ball bearings. What else do we have here? Of course, we'll eventually select our horsepower, right? And I picked a 7.5 horse. Okay. You can also pick the RPMs, so the nameplate RPMs, right? You can pick, they have a motor application as well. This was a farm duty, so we have a farm duty, right? Farm duty motor. And then you can pick the motor enclosure type, right? I think here I picked the totally enclosed fan cooled, right? So going through those aspects of the motor, we came out to a $1,500 motor. It's a little bit pricey, right? But it's going to do all the things that we want it to do. And it's going to be designed for the environment we're using it in. So I'm going to stop this video. We'll pick back up in the next video, and we'll look at considerations for the circuit we want to design for this motor. So we've now selected the motor. We want to then think about the circuit we're going to use to power the motor.